In this video, I'm going to be introducing you to something called sum and difference formulas, also sometimes called addition and subtraction formulas. Here on the left-hand side of this equality that I've written now, this is what I mean by a sum or a difference formula, or an addition formula. This is the sine of the sum of two angles. The first thing I'd like to do here is prove to you that this statement is true. I can give you a list of formulas and you can plug the numbers in, but I'd like you to believe that this is really true to start with. Now, I'm not going to do the kind of proof that we did in the previous video because this equation, this equality, doesn't lend itself to that kind of logic. I'll do what I can to line things up in the best way that I can to sort of make it look as much like that as possible, but I'm going to rely heavily on a diagram as well. I want to start with this. I'll assume that I'm in quadrant 1, and I'm just going to draw a big angle. Now, this angle here has a sine, and its sine is opposite over hypotenuse. But what if I want not the sine of a single angle, but the sine of the sum of two angles? Well, then I need to have two angles. So let me split this one up into two angles. And for now, I'm going to move this y and this vertical out of the way, and I'll move the r out of the way as well. Now I'm going to add a few lines and points to this graph. We'll start by labeling the origin O. Now that's a point O, like sometimes you see a point P with coordinates 3, 4, for example, but this is the point O with coordinate 0, 0. I'm going to draw a line segment between the outermost terminal ray and the smaller terminal ray in here so that it's perpendicular to this segment right here. So I'm going to have a right angle right here. I'll put that in. This is a right angle. I'm going to reintroduce my vertical line, but I'm going to put it here so that it meets the place where this right triangle has a corner, has an angle. And I'm going to put another one starting here and going down to the x-axis. So this is a right angle, this is a right angle, this is a right angle. And now I'm going to add one more line segment. I'm going to draw a horizontal line here, and if this is a vertical and I'm drawing a horizontal, it's going to introduce another right angle. Now, some of the points that you see where places where line segments connect are going to be important in what I'm going to do next. So I'm going to label some of these points. As it turns out, I don't need all of them, but I need most of them. So those are the points I care about, and I'm going to label them P, Q, R, S, and T so that I can talk about them. I'm also going to label my angles A and B. I'll call this one A and this one B. And with that, I can start talking about the left-hand side of my equality here. I'm given that the left-hand side is equal to the sine of A plus B. Now, remember from geometry that you can call line segments things like OR and ST, PQ or QS, depending on where you are. And it tells you that the name of that line segment, ST, tells you which 2 points it goes between, where it starts and where it ends. And if you know the coordinates of those 2 points, you can find its length. Well, we don't need that part here, but we are going to use the convention of calling a line segment by its name. The sine of the angle A plus B, this angle here, this big angle here is A plus B, is opposite over hypotenuse. But opposite is this line right here, PR, over hypotenuse, which is OP. So now I have a different way to think about the sine of A plus B. And because I now have this ratio of 2 side lengths, I can go back to my diagram and find all kinds of different ways to think about those. For example, PR has a point Q right in the middle of it. So I can think of that as PR as PQ plus QR. It's just the sum of those two line segments, the sum of their lengths. Well, I can unadd these two fractions that have a common denominator, and that gives me PQ over OP plus QR over OP. And I could also use a different length for QR. QR is here. And this is a rectangle. These are all right angles. So I can say, instead of QR, I can write ST. They're the same length. In the next step, I'm going to do a little bit of fraction unmultiplying. I have PQ over OP is the same as PQ over 1 times 1 over OP. And I have ST over OP is the same as ST over 1 times 1 over OP. Instead of writing it as 1, though, I'm going to write the first one as PS over PS. I have PS over PS. Now, all I've got here is two fractions, which when you multiply them together, have factors that will cancel in the numerator and the denominator. So I end up with PQ over OP, which is what I had here. I'm going to do the same thing here, except I'm going to use OS over OS. Now I want to take each one of these factors and see if I can figure out what it is in my diagram here. PQ over PS is this line segment divided by this line segment, or actually their lengths. Now I can think of the ratio of those two sides, PQ over PS, as the side opposite this angle divided by the hypotenuse, or the side adjacent this angle divided by the hypotenuse. So I'm going to give these angles some names. I'm going to call this one alpha and this one beta, because I can now either think of this as PQ over PS as the sine of angle beta or as the cosine of angle alpha. I can choose whichever one of those I want. Then I'm going to multiply that by PS over OP. I'll use a different color. PS and OP are this line segment and OP, this line segment. And so now I have either, from the perspective of B, the opposite over the hypotenuse, which means I have the sine of B, or I have the cosine of this angle up here. That seems like it's going to be messy. I have to figure out what alpha is, and then I'll have to figure out what this is. And once I know what B is, I can subtract that from 90, and that's way too involved. If I don't have to do that, I'm not going to. So I'm just going to call this one the sine of B as well. In other words, I'm only going to interpret that one, PS over OP, one way. Now, ST over OS, ST over OS, let's get a color. I think I'll do green. ST over OS is either, trying to get my pen back here, it's either the sine of A, because from here it's its opposite over the hypotenuse, or it's the cosine of this angle right here. I guess I could call that angle gamma, and then I could say that it's the cosine of gamma. And now I want to multiply that by OS over OP, and that's OS over OP, and that is, let's see, it looks like it has a B, would be the adjacent over the hypotenuse for angle B, so it's the cosine of B. Get a different pen. The cosine of B, or it would be the sine of this angle. So again, I'm not going to interpret that one a different way. It's too messy. So now I can rewrite this. This is sort of two options that I have here. I can write this as either the sine of beta or the cosine of alpha times the sine of b plus either the sine of A or the cosine of gamma times the cosine of B. Now, notice that if I choose to use the sine of A, then I have sine A times cosine B in this term right here. And that's part of the right-hand side of the identity that I'm trying to prove. So I'm going to go ahead and choose sine A. For the other one, I have sine B. I have sine B here. I need it to be multiplied by cosine of A. And I have cosine alpha, but not cosine of A, or sine of B. So now what I want to do is go back in and take a closer look at this angle here that I called alpha. Because if I could show that alpha really is just A, then I've got cosine A sine B. I've got, where is it? I've got the second term in my right-hand side. So I'm going to start decluttering here a little bit. I'm going to move all of this extraneous, well, it's not extraneous, I needed it at the time. Moving all of this stuff out of the way that I don't think I'm going to need, and I'll just get rid of that. And I'm going to relabel this angle alpha so that we know that that's the angle we're talking about. And we're going to explore just that angle now. Let's start by looking at this triangle right here. I know one of the angles in that triangle is 90 degrees. And I know the other one is alpha, and although I don't know what alpha is, I know that alpha plus this other angle over here add up to 90 degrees, because I have a 90 plus two more that add up to 90. That gives me 180. So I'm going to label this angle, oops, wrong color, label this angle as 90 minus alpha, 90 degrees minus alpha. Now, the reason that's important is that I also know these two angles, sorry, I'm getting my pointer wrong here. These two angles here, I'm looking at a bigger triangle now. These two angles here also add up to 90. So whatever this one is, this one plus this one have to equal 90. This one is the same as we had here. In other words, let me label it, how am I going to do this? This one is 90 minus, that's this whole right angle right here, 90 minus this one right here. Well, that one right there is 90 minus alpha. So what's left, this angle right here, is 90 minus 90 minus negative alpha. That means that this angle is also alpha. Now that's kind of roundabout, but it's what we need. There's one last thing we need to do here. Let me take a few things out and relabel this alpha, and then I'll come back. Oh, okay, I hope that is a little clearer. That angle right there is alpha degree. Now I can't get my alpha to move. Is alpha degrees. And that means it's the same as this angle up here. Well, that's not what's important. What's important is that if I draw two horizontal lines and a transverse, then the alternate angles that result from that construction are equal. And that's a fact from geometry that you may or may not remember. That's okay. But the point I need to make here is that this angle right here, which I have labeled alpha, and this angle down here, which is angle A, are the same size. So if A is equal to the cosine of alpha, and what that means is that I can change cosine alpha to cosine A. Oh, I erased a little too much there. Now, I can take either sine B or cosine alpha, sine B or cosine A. Sine B is going to be sine B. Cosine B is fixed for both of these. And I've already chosen sine A. So I'm just going to choose, first of all, cosine alpha over sine B, and then I'm going to rename it cosine A. So ultimately I have that this is equal to cosine A sine B plus sine A cosine B. And because I want this to be exactly the same as I had in my right-hand side, I'm just going to change the order of the terms. Addition is commutative, so I can do that. So now I have the sine of A times the cosine of B plus, I did have cosine A sine B, but again, I can change the order of the terms, or the order of the factors. Multiplication is commutative as well. So I'm going to write it as sine B cosine A. And that is my right-hand side. Now, this proof is a little bit different. In fact, it's a lot different. I've done the left-hand side, right-hand side thing, and all of my equal signs match up. This step was a little weird, but I was just using it to demonstrate something. So you could almost argue that I went from there to there instead. Now, but along the way, I had to use this diagram to make all of these points. I couldn't just say PQ plus QR over OP if I didn't know what PQ, QR, and OP were. I had to set up this diagram so that I would have some way to reference what those values were. But this is actually a classic proof of the sine of A plus B equals sine A cosine B plus sine B cosine A. But one of the other points that I want to make here is that because of the commutativity of addition and multiplication, I don't really need to write this last step down. I would argue that it's the same as the step above it. So I could, in fact, have stopped here and said that that's equal to my right-hand side. I know I said at the time that it had to be exactly equal, but it doesn't have to be exactly equal as long as it's equivalent. What you see on the screen now is the result of an explanation. It is something of a formal proof. I started with my left-hand side. I worked my way out, down through the logic until I got to the right-hand side. But there are a couple of steps in here that I wouldn't necessarily include if I were writing it up as a formal proof. And those are this step here and this scratch work here. It doesn't actually matter if I can choose between two different ways to say ST over OS. Let's see, where was that again? ST over OS. It doesn't matter if I can think of two different ways to say it. I have one way in particular that I need for it to be said. So I can actually just leave this part out. And the same can be said for cosine of B. In that same term, I have two copies of the cosine of B. Well, one will do. This used to be cosine alpha before I changed it. But in order to change it, I had to demonstrate that alpha and A were the same size. So instead of sine B, sine of beta, or cosine of alpha, let's just go with cosine of alpha. And then sine of B is sine of B. It's the same for both of them. So I don't really need this or nonsense. I did that on purpose at the time to help explain a lot of stuff that wants to move one thing at a time here, so that I could explain what it was that I was doing. But if you were reading this proof on your own, this would really be all you would need. So that's the kind of thing I would expect to see on a quiz or an exam. You can actually put this down here and this down here. I've got it all in one line, one column. So the only thing that is wrong with this one at this point is that this cosine alpha hasn't been adequately defined yet as cosine of A. So here you might even say, because alternate angles are equal. That justifies the fact that these two are the same, and that lets me write cosine A sine B plus sine A cosine B, and that equals the right. This comment here might actually be better on this line, just because what I'm saying as I read this, if I were reading it aloud, I'd say that these ratios plus these ratios can be thought of as cosine alpha sine B plus sine A cosine B, and that line is equal to this line because of alternate angles, right? This is true because of this and alternate angles, right? Because alternate angles are even. Now, there's a lot on the screen here, and there was a lot, it's taken me 20 minutes to do this proof for you. I'm actually not going to do the same thing for all of the other formulas. I may, from one topic to the next, decide to prove a particular formula for you. I'll try to do the ones that are not also in your textbook, so you're not seeing the same thing that's already in your textbook. You should be able to follow along with your textbook. But for now that you know how something like this might be proved, let's go ahead and make a list of all of the formulas we're going to be using in the rest of this topic. We already know this formula. This is the one we've been working on for the last 20 minutes. The sine of the angle comprised of the sum of A and B has the same numerical value as the sine of A times the cosine of B plus the sine of B times the cosine of A. Once you know what the angles A and B are, you'll literally just plug them in. The nice thing about this formula is that if you think of B as being a negative number, you can get the sine of A minus B, and then you have the sine of A cosine of B minus the sine of B cosine of A. Now, the way I like to read these is that if your plus is on the top, you're kind of following along the top, then you follow along the top on the right-hand side as well. If you're following along the bottom, you get the minus here, then you get a minus here as well. Now, that seems obvious now, but in a few minutes, we're going to talk about a formula where it's not quite so obvious, and I think that will help show, sort of direct which way you're supposed to go. This takes up a lot less room on a note card than having the formula written out twice, where the only difference is the sign here and the sign here. The next one is the cosine of the sum of two angles. And that's equal to the cosine of A times the cosine of B. And then we have the sine of A and the sine of B. But where the sine has a sum here and a sum here, the cosine has a sum here and a difference here. There we go. Now, if I want to do plus or minus here, I can do that. But notice that if I'm following along the top, I get to a plus first here and a minus here. But if I'm following along the bottom, if this is a minus, then this is a plus. So plus or minus is not necessarily equivalent to minus or plus. The formula for tangent is a little bit different. It's the tangent of A plus B is equal to the tangent of A plus the tangent of B over 1 minus the tangent of A times the tangent of B. And if I make a plus or minus here, then I'm going to get a plus or minus here and a minus or plus down here. Again, if I'm following along the top, then I'm looking for the sum of two angles, the tangent of a sum. If I use the plus sign from here, I must use the plus sign from here, but the minus sign from the denominator. Okay, I think it's time we took a look at a couple of examples. We'll start with the sine of pi minus x. Well, this is a difference formula, but it's the sine formula that we want, where a is pi, b is x, and I have a minus between them. So at this point in your career, I'm not asking you to prove this formula. I may ask you to prove some of them, but for right now, I'm not asking you to prove this. I'm just asking you to use it. So I'm going to take the sine of pi minus x and rewrite it as the sine of pi times the cosine of x minus the sine of x times the cosine of pi. Now, I know what the sine of pi is, and I know what the cosine of x is. From my table, or from a unit circle, or however you remember it, the sine of pi is 0, and the cosine of pi is 1. So now I have 0 times the cosine of x minus 1 times the sine of x, and that's my answer. Now, to be blunt, this is kind of an exercise. You don't actually see these terribly often in the field, but that's how you would use this formula. Let's try a slightly different one. Let's do cosine of 3 degrees times the cosine of 44 degrees minus the sine of 3 degrees times the sine of 44 degrees. Now, first of all, you'd have to recognize that this is the right-hand side of my cosine formula, like the sum of cosines, sum or difference of cosines. It's the right-hand side. So because I'm given it in that form and asked to simplify, I'm going to write it as the left-hand side of the formula, which is the cosine of 3 and 44. Put my degrees on there. And if I have a minus in the long side, the long version of the formula, then I have a plus in the short version. So that gives me the cosine of 47 degrees. Now that's still not a nice angle, so there's not really much I can do with that, but I have written it as the trigonometric function of one number. Sometimes you'll be given something like the cosine of 75 degrees, and you can find the exact value of the cosine of 75 degrees without using your calculator, because the cosine of 75 degrees is the same as the cosine of the sum of two angles. Now I can use this any two numbers in my sum, right? I could say 71 and 4. But what makes sense here is to use 45 and 30. Because I know the cosine of a sum of two angles is equal to the cosine of the first times the cosine of the second. I have the sum, but it's a cosine, so I'm going to have a minus here. The sine of the first, the sine of the second. Running out of room. But I know what the cosine of 45 degrees is. It's square root of 2 over 2. And I know what the cosine of 30 degrees is. It's square root of 3 over 2. And the sine of 45 degrees is root 2 over 2. And the sine of 30 degrees is a half. So I can evaluate this, root 6 over 2 minus root 2 over 2, common denominator. So I have root 6 minus root 2 over 2. Sure, I can stick it in my calculator. I can just plug this into my calculator, but I'll get a decimal. If I want to know the exact value, I can sometimes figure out how to write the large angle as the sum or difference of two other angles, and then I can evaluate each of these individual pieces and get an exact value. Be prepared to be able to work some of these problems in radians as well. We've kind of been stuck working in degrees for a while now because our entire last chapter on applications, most of it was in degrees. But you will see problems in radians as well. So don't forget about your values of cosine of pi over 2, or sorry, cosine of pi over 4 and cosine of pi over 6, sine of pi over 4 and sine of pi over 6. Now that we know these formulas, we can also use them to do proofs. We can use them to prove identities. Let's do that on the next screen. We've been asked to verify here that the sine of some angle theta plus 30 degrees minus the sine of theta minus 30 degrees is equal to the cosine of theta. Since we're doing a proof, I'm going to start by writing left-hand side equals, and then I'm just going to copy and paste the left-hand side. That is equal to, I have a new way to write the sine of the sum of two angles and the sine of the difference of two angles. So I'm going to use that. I'm going to write this as the sine of theta times the cosine of 30 degrees plus the sine of 30 degrees times the cosine of theta. That is this sine, this term. Now I'll do the same thing for the second term. The sine of theta minus 30 can be written as the sine of theta times the cosine of 30 degrees minus the sine of 30 degrees times the cosine of theta. Notice that I put the second term in parentheses, but because I'm going to be subtracting it from the first term, I'm subtracting the second term from the first term. So I put that in parentheses because I've got multiple terms within this term, and I don't want to forget to distribute my negative. Now, the next step is just a little bit of algebra. I have the sine of theta times the cosine of 30 degrees plus the sine of 30 degrees times the cosine of theta. And distributing my negative, I get minus the sine of theta times the cosine of 30 degrees plus the sine of theta, the sine of 30 degrees times the cosine of theta. Now, within this expression, within this long expression, there are 4 places where I can evaluate the sine or the cosine of 30 degrees. So that's the next step that I'm going to take. I'm going to rewrite this. But instead of writing sine of theta cosine of 30 degrees, I'm going to write the sine of theta times what I know the cosine of 30 degrees to be, which is the square root of 3 over 2, plus the sine of theta, the sine of 30 degrees times the cosine of theta. Well, the sine of 30 degrees is a half, and so on. The cosine of 30 degrees is root 3 over 2. The sine of 30 degrees is a half. And actually, as I look at this line here, I'm realizing that I could have thought of this as sine theta cosine 30 minus sine theta cosine 30, and I could have canceled those right from here, and then I wouldn't have to have done those evaluations. But it's not wrong to have done it the way I did either. I can see in this step, for example, that now I have the sine of theta times root 3 over 2, and over here I have the sine of theta minus the sine of theta times root 3 over 2. So those add up to 0, so they cancel out. And what's left is half of a cosine of theta plus another half of a cosine of theta. So that's a whole cosine of theta. And that's what I was aiming for. That's what my right-hand side is. So now I'll write equals right-hand side. Working with the cosine formula, the formula for the cosine of the sum of two angles isn't much different, except that you do have to make sure that you get your identity right. Just as a reminder, the cosine of the sum of two angles is the cosine of the first times the cosine of the second, and the sine of the first times the sine of the second. And where you have a plus here, you have a minus here. Other than that, it's usually a case of plugging in or using this fact, if you will, to prove something else. So I'm not going to do any of those problems just in the interest of time, but I am going to do one that deals with the tangent, because that one's a little trickier. All right, here we've been asked to find the exact value of the tangent of 7 pi over 12. Now, if I stick this in my calculator, I'll get a decimal approximation, and I might get a really pretty good one. I mean, I might get a decimal approximation to 8 or 9 or 10 decimal places, but that's not an exact value. So let's see if we can figure out a different way to write 7 pi over 12 so that I can take the tangent of some more familiar angles. One way to think of 7 pi over 12 is as 3 pi over 12 plus 4 pi over 12. And that simplifies to pi over 4 plus pi over 3. So 7 pi over 12 is just pi over 4 plus pi over 3. So now I'm not proving anything this time, I'm just evaluating, so I can write the tangent of 7 pi over 12 is equal to the tangent of pi over 4 plus pi over 3. And I have a formula that tells me that this is equal to the tangent of pi over 4 plus the tangent of pi over 3 all over 1 minus the tangent of pi over 4 times the tangent of pi over 3. Well, I can evaluate these quantities. I know what the tangent of pi over 4 is. I know what the tangent of pi over 3 is. I have 1 minus tangent of pi over 4, tangent of pi over 3. The tangent of pi over 3, the tangent of pi over 4 is the sine of pi over 4 over the cosine of pi over 4. But those two values are the same. They're square root of 2 over 2. So the tangent of pi over 4 is 1. The tangent of pi over 3, I can never remember this one. So I have 0, 1, 2, 3, 4, the square root of, this is my sine, and 0, 1, 2, 3, 4. Pi over 3 is, let's see, that's 0, pi over 6, pi over 4, pi over 3. So it's this column here, and I'm looking for the tangent. So I go down this column, I want the sine over the cosine. So it's the square root of 3 over 2 over the square root of 1 over 2. And then the 2's, because they're the same, cancel. So it's root 3. So that's what goes in here. Of course, you can look that up in a table if you prefer. I just find it pretty easy to, I've got all these little mnemonics, right? I just know it's sine over cosine, and I know it's this column, and I know my values. So I just kind of play around with it until I figure out the values that I need. Sine over cosine. All right, now the rest of this is arithmetic. I have 1 plus root 3 over 1 minus 1 times root 3. And that is the exact value of the tangent of 7 pi over 12. As usual, there's a lot more we could do here, but I think that covers the bases, at least at a basic level. So I'm going to leave this video and we can move on to the next one. In the next video, we're going to be talking about evaluating expressions involving inverse trigonometric functions. But we're in the section called addition and subtraction formulas. So we're going to be using addition and subtraction formulas to do some of that work.